So we will. I hope you enjoyed the kind of the section on neural networks. I always thought it was kind of neat, and it's a good application of using the gradient descent algorithm to minimize a loss function. Okay, and so anyway, when we were looking at our textbook, chapter 1 was we looked at a way to estimate our parameters or train our model by minimizing a loss function. So let me just, chapter 1, we trained our model, or in other words, estimated parameters. Okay. By minimizing a loss function. Okay, so that's what we did in chapter 1, and we saw, we could minimize the loss function using gradient descent, things of that nature. And today we'll enter into chapter 2, and we will train our models this way. We will train our models by maximizing likelihood. Likelihood function. Okay. So just keep in mind, loss function starts with an L, and likelihood function also starts with an L, but they're very different things, okay? So here we're going to train our models by maximizing the likelihood function, and so this is called maximum likelihood estimation. Or MLE, and you might have covered this in 100B already. We will take a look at it again today in the context of training models. Okay, and so again in this case we'll just start with the simple linear regression example, because I think it gives us an idea of just the idea that we have a model of our data and we're trying to estimate parameters. Okay, so again, we will use linear regression. We'll use linear regression as our example. So again, in chapter 1, we were trying to minimize the loss function, which we defined as the sum of squared residuals. This time, we are going to write our model as we're going to have a generative model. Okay, so we use and in a generative model, we include an error term. Okay, and basically we include an error term, and our model tells us how our data might be generated. So we might say some observation. So observation value, what this is equal to the value from the mean function plus some random error. And so in our case, we might say some observation, t sub n, our observed value, this could be equal to, you know, I'll just write mean function again, plus e sub n, or epsilon sub n, okay? And we will say, you know, the errors, we can say the errors come from any function, but we will say the errors here will come from a normal function. So our errors from a normal distribution. Have you guys taken 100C, generalized linear models? Okay, and in that class you learned you can have errors coming from different distributions, right? Not necessarily the normal. The normal is a good choice for a lot of things, but you can also have, you know, other, you know, binomial distribution for your errors, okay? Just from some exponential family, right? Okay, and so for linear regression, our mean function is, this is going to be w sub 0 plus w1 x sub n, and then we'll leave this random error. This will still come down plus e sub n. So now this is our generative model. We're going to say for linear regression, we model our mean function as having a linear relationship to x, and then we add in some kind of error term. Okay. And so if we say, so we can just kind of maybe formalize this a little bit. We will say t sub n is the vector x is a function of the x sub n given model parameters w. So, you know, a function of x given model parameters w plus some error value e sub n, and we will say e sub n comes from normal distribution mean 0 sigma squared. Okay, we can, this part can be written as w transpose x sub n plus e sub n. We can also write this as well. Okay, and because this is now this is the normal distribution, and this is going to serve as our mean. Okay, this can serve as a the quote mean of our normal distribution. So we can also write that t sub n, or I'm sorry, that the probability of t sub n given the values x sub n, w, and sigma squared is equal to the normal distribution where it's centered. The mean is w transpose x sub n times sigma squared. Okay, and then just recall the normal density. So if some value y comes from with mean mu sigma squared, this is 1 over sigma root 2 pi e to the negative 1 over 2 sigma squared y minus mu squared, right? So that's the normal density right there. Okay. Is everything so far so good as far as what we're modeling? And so visually, what we can think of is, let's say we have, you know, some kind of data like this, okay? Basically, we're gonna model this as, we're gonna say, okay, there is some line like this, okay? This line represents you know, W transpose X, X, or X of N, okay. And then at any given spot here, we can say there is a normal model centered right here, okay? And the values that we might observe are distributed with this mean, okay? So that, you know, there's another, let me say there's something like this. Yeah, I'm struggling here, okay? So that it's centered right there, okay? And so all of these, you know, this is, you know, normal with this mean, and standard deviation or variance sigma squared, okay? And that's kind of the idea. This is, we're saying, you know, given some value x, we can kind of create a generative model. And so, you know, for a particular value of x, we can say, well, according to the mean distribution, we would expect the center to be, you know, at some location right here, and then we would expect, you know, values to be generated from a distribution coming from this thing. So I'll use a numeric example coming from our textbook, where you know, we're looking at the race times, Olympic race times, and so based on the year the Olympics were held. Okay, so we got numeric example. Okay, and we are looking at race times, okay, as a function of the year of the Olympics. Okay, and so it looks something like this. Okay, and then we're going to look at the year 1980. Okay, and then so for the year 1980, our vector x of n is going to be 1, 1980. Okay, and this is because our w vector of coefficients has an intercept and a slope, right? So our intercept is 36.416 and our slope is negative 0.0133. And we will just arbitrarily use sigma squared is 0.05. Okay, so these were just somehow, you know, these are provided to us. Okay, and thus we would say the probability of a particular value in the year 1980 given x sub n, w, and sigma squared is going to look like a normal distribution w transpose x sub n transpose sigma squared. Okay, and so this part becomes w transpose, so 36.416 comma negative 0.0133 times the 1980. Okay, this is our mean, and then we get sigma squared, which is 0.05. And so when you multiply this out, you get 36.416 minus 1980 times 0.0133, which equals to 10.02, and sigma squared is equal to 0.05. So this probability of t sub n given x, w, and sigma is the normal distribution centered at 10.02 and standard deviation equal to 0.05. Okay, and so what we're saying is that right here is 10.02, and I have a normal distribution centered right there. And whatever value we observe, we can calculate the probability of getting that value. Is this okay? Okay. And so now that we have a model of how our data is generated, and the model itself is includes this this probability density, we can calculate the likelihood of every single data point, right? So based on this, we can calculate the likelihood of the actual data point, or the probability of the actual data point, which was, I don't know if I have it right here. In 1980, the actual time was 11.06, and so we can see, what's the difference between that and, or wait, maybe it wasn't 11.06. Oh, here it is. 10.25, okay, so the actual y is equal to 10.25. We can calculate the density for this value. Okay. And we can calculate the density or the probability values for every single observation that we have. And thus we can get our likelihood. Okay. So again, the density, one thing to, when you take your intro stats class, they never teach you how to calculate the density. They always just, right, so you have this normal model. In the intro stats class, we always teach you, like, for some particular value, like right here, we always teach you the area to the left, but the density is the actual height of the value right there, right? Actual point on the curve, which we've established, okay, to be 1 over, probability of y given some value mu sigma squared. This is 1 over sigma root 2 pi e to the negative 1 over 2 sigma squared y minus mu squared. Okay, so let's talk about our likelihood. The likelihood function. Do not confuse with loss function. Okay, so the likelihood function, which I'm just going to call L here. Yes?
Using y as the height or y as the...
Y is here. This is the y. Okay, sorry. Mu and y. But, so this here is the actual point. This would be probability of y given mu and sigma. Okay, that's the height. The height is the probability. The y is the location right there. Okay, and so the likelihood function would be the probability of our data, right? So this is all of our data. You know, as a function given our X matrix and our W estimates. Okay. It's important that you know, I guess one condition is that our data, our observations are independent of each other, okay? Our observations must be independent of each other. Okay, so this is what we have here. If all of our values are independent of each other, then the total likelihood of the entire data set is the product of each probability multiplied together, right? If the probability of one is this, then we, you know, so the probability of each observation is given by our density function. Given that particular value of x, the estimated, or the parameters w, and our sigma squared here. So this is the product there. And because, you know, for linear regression, this thing is normally distributed around normal distribution around W transpose X sub n, sigma squared. Okay. So for, you know, for linear regression, our values come from this normal distribution. Okay, so we have this normal distribution, and so this is where things get ugly. We're going to have to plug in all of this into here, okay? So keep in mind, this is still our likelihood function, right? Is the product of every single data point's probability multiplied together, okay? And this is going to be 1 over sigma root 2 pi times e to the, and in this case I got negative 1 over 2 sigma squared. That's fine, okay? And then what do I have? My y is my observation t sub n, and then the mean is the W transpose X sub n, right? So this is, now we have the product of all of each observation's probability. So this is my likelihood function. Okay, so the likelihood is the product of all observations' densities. Is that good? Okay, and so this is the function we want to maximize our likelihood. So we want to find the values of W that maximize this likelihood. And so that's the entire premise of maximum likelihood estimation here. Okay, can I flip to the next page? Okay, so I have all of this, and we want to maximize this function. Okay, so we want to maximize the likelihood function by finding the correct values, finding, I don't know, the quote best values of W. Okay, so the best values of W will be the values of W that maximize this likelihood function. All right, so what should we do? Okay, well, to maximize some kind of function like this analytically is quite tricky, okay? Because we have a product. This is a product of everything, and so it's going to be, it's hard to do that, okay? It's hard to take the derivative of a massive product. So to simplify our lives, we use the log likelihood, okay? So to make derivation easier, we will take the log of the likelihood. Okay, and the log is what we call monotonically increasing. So the maximum of the log of a function is still going to be the maximum of the function itself. Okay, so the log function, the log is monotonically increasing. This just means, which basically just means if A is greater than B, then f of A is greater than f of B for all A and B. That's what monotonically increasing. Okay, so the log is monotonically increasing. So the values that maximize the log likelihood will maximize the likelihood. Okay, so the log likelihood, so which we will just write the log L. Okay, so now I just take the log of this thing. Okay, so the log of a product becomes the sum of the logs. So I'm going to go from 1 to n, and basically it's just going to be the log of all of this, right? Okay, so what's the log of our first term? Well, the log of division becomes subtraction and multiplication becomes addition. So I'm going to have log of 2 pi, okay? But this is raised to the 1/2 power, and it's on the bottom, so I'm going to have a negative 1/2 in the front there, okay? And then I'm going to just separate out the sigma out here, just to keep my life a little easier. So I'm going to have log of sigma, okay? But there's that first term. And then the log of the exponent of e is just the thing, so, or actually it's negative on the inside, so I'll leave that off. 1 over 2 sigma squared of t sub n minus wt x sub n squared. I think this is what we have, and this is all inside the summation. Let me just make sure my math is correct. Okay, yes, that looks good to me. All right, and then so if we look at this, none of these values depend, as far as this thing goes, none of these values depend on n. Okay, it's going to be the same for all n values. So this is just going to become a product. Okay, so this is going to be negative n, capital N, times all of this. And then same thing here, minus n log of sigma. Okay, because all of these values is the same for every n. This part also does not depend on n, so I can pull that out of the summation. And then now the summation just goes on the inside term here. So this is n equals 1 to n of t sub n minus w transpose xn squared. Okay, so now we've taken the log. This is our log likelihood function. What a pain. All right, and then and now we're going to take the derivative of this so we can maximize it. Okay, because we're going to find where the derivative equals 0, and then we will say that's either going to be a local min or a local max, and we'll look at what that is. Okay, so we take the log derivative of this, take derivative to maximize. Take derivative, set equal to 0 to find the local min or local max. All right, so the derivative of this with respect to w, okay, well, this thing, that's 0. This thing is also 0, okay, and now I just have this to deal with. Okay, so I got 2 sigma squared, okay, and then taking this down, this is a square, so I'm gonna I've got a 2 here, and then we apply a chain rule. So now I have to multiply it by the derivative of what's on the inside. So that's going to be negative xn. Okay, and so just rearranging some stuff around. This 2 is the same for everything, so I'm going to just have and then the negative comes out, so I have 1 over sigma squared times n equals 1 to n of x sub n times tn minus w transpose xn. Okay. All right. And so this is still, we're trying to find the derivative of all of this. Okay. Now, just to, I'm going to distribute the xn term on the inside here. And so this will give me xn tn. Okay. And when I bring this over here, to make my life easier later, I'm going to do some rearranging here. Okay. So what we're going to do is, if we look at w transpose xn, okay, what are the dimensions of this? Okay, so w itself is a 2 by 1 vector, so w transpose would be a 1 by 2, okay, and then xn is a 2 by 1 vector as well. Okay, so this just becomes a scalar. Okay. And so because it's a scalar, then I can swap these terms around, and you can verify that if I swap these terms around and add them up again, this is also going to be a 1 by 1 scalar, and these two things would be equal. So I'm going to just I'm going to stick this back in here, and then when I distribute the xn, I'll have xn xn times xn transpose w. Okay, and then we can just double check and make sure all of the dimensions line up here. X sub n is 2 by 1, xn transpose is 1 by 2, and then w is 2 by 1. Okay, and so when we multiply all of this out, this becomes a 2 by 1 vector, right? And then if I look over here, x sub n is 2 by 1, and t sub n, I'm sorry, xn, yeah, t sub n is a 1 by 1, and so this remains 2 by 1 as well. Okay, which works because we're adding these, so these dimensions need to be the same. 2 by 1 subtracted from another 2 by 1. Okay, the reason why we bothered with all of this was so that we could put the next step into matrix notation. Okay, so over here I'm going to say, just say that x is equal to, you know, it's 1, x1, 1, x2, dot, 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 1 through xn, or in other words, we got x of 1 transpose, x of 2 transpose, all the way down to x of n transpose. And because of that, we can say that the sum of xn tn, if we think about this, this is going to be big X transpose t, or the vector t. Okay, so if we think about x, what all of these things are, we can say everything multiplies out together. So we can replace this part with big X transpose t sub n, or not t sub n, t vector. And then, and if we also do some more substitutions here, we can see that the sum of xn, xn, w, xn transpose w, this becomes x transpose x w. I know. These are good. These are kind of good identities. To know. Okay, and so this becomes x transpose x w times 1 over sigma squared. This is my derivative of the log likelihood. Okay. So I've got this. Now I want to set this equal to 0, and then we're going to solve for w. Yes?
Just for clarification, what does the t vector, or what does the t value represent?
The t vector is kind of like our y's. Our textbook notation, for whatever reason, they use t as instead of y. I don't know why, but they do that. So this is so the t's there are the observed value.
So the t sub n is just an individual.
T sub n, yeah, is an individual value, right? So, you know, in the year 1980, our T sub n was, I don't know, 10.26 seconds. Okay, and then X sub n would be 1980. Okay, so now that we have this, now we're going to set this equal to 0 and solve for W. Okay, so we'll set this equal to kind of the 0 vector, because this is, what are the dimensions of this? This is a 2 by 1, right? So this is a 2 by 1 0 vector as well. Okay, so we, set to 0, solve for W. Okay, so I just multiply both sides by sigma squared, and now I have x transpose t minus x transpose xw is equal to 0. Okay, and I can just move things around, and I have x transpose t is equal to x transpose x w. And so solving for w, I just get x transpose x inverse x transpose t is equal to w. Okay. And so if this is going to be our estimate, so our estimates, we'll set it equal to our w hat. These are, our estimates that maximize the likelihood of our data. Okay? And we notice that these estimates of W are the same as the values that minimize the sum of squares residuals. Okay? These are also okay, so in the last chapter, we were looking to minimize our loss function, which is the sum of squared residuals or the average squared residuals. In this chapter, we were looking to maximize the likelihood, and we ended up with the same solution. Okay? That's not always going to be the case. It ended up the case this way because if we look at the density function of the normal distribution, if I can skip back here, inside the density function of the normal distribution, there's something that looks very similar to the squared residual term. Okay, so that's part of the reason why we end up arriving at the same solution. But that's not always going to be the case. Okay, and we can do the same thing. We can solve for the values of sigma squared that maximize the likelihood. Okay, so we can estimate sigma squared to maximize our likelihood. Okay, and so in this case we would take the derivative of our log likelihood with respect to sigma. Okay, and if we do this, I get 1 over n sigma plus 1 over sigma cubed, the sum of t sub n minus the vector x transpose w squared. Okay, we can set this equal to 0, and then solving for sigma squared, you get what do I get? I end up getting sigma squared is equal to 1 over n t sub n minus x transpose w squared. Okay, and then we can we can use our estimated values of w which are, W hat, okay, to get an estimated value of sigma. Okay. So this will be the value of sigma squared that maximizes our log likelihood. And if you look at this is pretty much the 1 over n of the sum of effectively y minus mu squared, right? So this is kind of effectively, it's kind of our term for variance anyway, right? The difference between each value and the mean, except this time our mean is a function of x, okay? All right, and so this establishes just another approach that we can use to try to train models. So last chapter we were looking to train models by minimizing our loss function. This time we can train models by maximizing the likelihood of the data. Okay, so we want to find the model parameters that will give us the greatest likelihood of getting the data that we've observed. Okay, and so this opens up a new avenue, and so we'll explore this a little bit more on Wednesday, and we'll go from there.